In my last video, I talked about confidence interval estimates in general, and specifically confidence interval estimates of the population proportion. In this video, I'd like to focus on estimating the population mean. Now, I went through a general explanation of confidence intervals in my last video, so I'm not going to do the same thing here. I'm just going to jump right into confidence interval estimates of the mean. So one of the things that I discussed in my previous video, that the confidence interval is basically saying that the population mean is somewhere between our point estimate plus or minus the margin of error. So between x bar minus e and x bar plus e. And that e, that margin of error, is coming from the critical value times the standard error. Now, there's going to be two types of critical values that I'm going to discuss in this video. One's coming from the normal distribution, and one's coming from a new distribution that we haven't yet discussed, and that's the t-distribution. So we're going to have two formulas for margin of error, both structured the same way, critical value times the standard error. But in one case, we know the population standard deviation, and in the other case, we don't. Now, this is the case where we don't know the population standard deviation. That's the one that actually occurs in reality almost exclusively. 99% of the time, if we're estimating, if we don't know the population mean, how can we know the population standard deviation, right? But we're going to talk about both. We're going to talk about both cases in this video. Okay, and just like with the proportion, you can express the confidence interval as an inequality. You could express it as a point estimate plus minus the margin of error, or you could express it as an interval. So three ways of saying the same thing. And so, for example, let's say you have a random sample of 104 light bulbs and with a mean life or an average life, how long they last, of 543 hours. And let's assume you know that all such light bulbs out there of the same type have a population standard deviation of 26 hours. Construct a 90% confidence interval estimate for the mean life of all such light bulbs. Now, I'm not going to solve this problem in this video. You might want to pause this video now and watch my video solution to this problem. I do it on Excel. And then come back to this one, or you could watch it after this video, either way. But definitely you want to watch the video for the solution to this problem. All right, so this example goes through the case where we know the population standard deviation. So there's only one unknown here. The unknown is mu, is the population standard deviation. Now, if we don't know the population mean, and we also don't know the population standard deviation, well, now there's an extra unknown there in the system. So we need an estimate that's a little bit more forgiving, that it takes into account some of that extra inherent error based on that extra unknown. And so for that, we're going to use a new distribution, which is very similar to the normal distribution, and this is called the t-distribution. And the t-distribution depends on the sample size. Remember, the normal distribution, there's only one version of it. There is the normal distribution, and that's it, for any size sample, any size population. So now, when we don't know the population standard deviation, we're going to use the t-distribution. And this, again, this accounts for extra error in the system, and it is dependent on sample size. So, number one, if you know sigma, use the normal distribution. The t-distribution is only for the case where you don't know sigma. Now, you'll use the same test statistic. Now, test statistics I'm going to talk about later in the context of hypothesis tests. They don't really apply here to confidence interval estimates. And like I mentioned before, there's only one version of the standard normal distribution, but there's different versions of the t-distribution based on the sample size. Okay, so one definition, a term we have not used yet, is degree of freedom. So the degree of freedom for a collection of sample data is the number of values that could vary after certain restrictions have been imposed. Now, this is not always the formula for degree of freedom. This is just for this specific case. Later topics in different contexts will use different formulas for degree of freedom. But for confidence interval estimates, this is only for confidence interval estimates of the mean, the degree of freedom is just n-1, and that's it. One less than your sample size. If you have 100 in your sample, you have 99 degrees of freedom. Now, I'm going to give a quick example to sort of explain what I mean by freedom here. So let's say you give me, let's say you have a set of 5 numbers. So 5 numbers, 1, 2, 3, 4, 5. And when you average them out, the average must be 80. You're free to pick any 4 numbers you want. As long as you leave me free to pick that last number, I can make sure to give you a mean of 80. So for example, let's say you have these 4 numbers. You pick 19, 44.6, negative 91, and 50. I can make sure that the 5 numbers average out to 80 by choosing the right last number, as long as I'm free to pick one of the numbers. So basically, I could solve, to find the average of 5 numbers, you add them up and divide by 5. So that 5th number right here is the unknown. So I could say, take your first 4 numbers plus x divided by 5, and that must equal 80. And if I solve this problem, if I solve this equation, I'll get 377.4. And so that's it. If I'm free to pick that last number, 377.4, then the average value, or the mean of that sample, will be 80. Okay, so that's what I mean by degree of freedom. So there's n-1 degrees of freedom. As long as you leave me the freedom to pick one number, I can give you a mean of whatever you want. So now let's talk about the t-distribution. 1, it's different for different sample sizes. 2, it has the same general shape of the normal distribution. Now, if you look at a graph of the normal distribution and a graph of the t-distribution, if they're not labeled, you can't tell them apart. They look exactly the same. They're very, very similar. The mean of the t-distribution, just like the standard normal distribution, is 0 and the standard deviation is 1. The standard deviation is always greater than 1. So as the sample size approaches infinity, as your sample sizes get larger and larger and larger, the standard deviation gets smaller and smaller and smaller, it gets closer and closer to 1. So as n gets larger and larger, the t-distribution gets closer and closer to the normal distribution. So let's look at what the graphs of these distributions look like. Here we have the standard normal distribution in blue and 2 different versions of the t-distribution in orange and red. So you look at when your sample size is n equals 3, you get the orange graph. And for a larger size, n equals 12, you get the red graph. So notice, as you increase the sample size, these graphs are getting closer to the blue one, closer to the normal distribution. All right, so it's important to choose the correct distribution. Now, when we've talked about estimating the proportion, we've talked about estimating the mean when we know sigma, and we've talked about estimating the mean when we don't know sigma. So when you know sigma, when you know the standard deviation of the entire population, and one of these 2 things is true, either the population is normally distributed or your sample size is larger than 30. We've talked about this in my previous video. use the Z distribution, use the normal distribution. If you don't know sigma, and again, either the population is normally distributed or n is larger than 30, you use the T distribution. That's what I'm talking about now. And if those requirements aren't met, so if the population is not normally distributed, or your sample size is 30 or below, we can't use these methods. We use other methods called non-parametric methods or bootstrapping, and that's sort of beyond the scope of this particular class, so I'm not going to talk about those. So I'm going to focus on when we know sigma, when we don't know sigma, and when these criteria are met. I'm not going to talk about how to find the T values in this video. I have a separate video that I use Excel for the T distribution and finding those T values. I recommend definitely watching that one. So on this last slide, we have a problem where we're going to use the T distribution. So the specific absorption rate, or the SAR for cell phone, measures the radio frequency energy absorbed by the user's body when using a handset. Basically, when you hold your cell phone up to your head, your body is absorbing power. And that's what the SAR tells you. Your phone emits radiation and it's absorbed by your body. And so over here in this little table, we have the SAR rates, or how much power you're absorbing from 30 different cell phones. So what I want to do is construct a 95% confidence interval, or estimate with 95% confidence the mean specific absorption rate, or the mean SAR for all cell phones. And so for number one, we don't know the population standard deviation. And then for number two, repeat the problem. And how would that interval change if we knew the standard deviation for all cell phones, not just the 30 in this sample, but for all cell phones, was 0.403. And I go through this solution in detail using Excel on a separate video. Definitely want to click on that link to watch that video. And that about does it. That's it for my discussion of estimating the population mean.